No, I can't. We're not going to do that. So, come on. There we go. So, my name is Kyle Kingsbury. You might know me as Afer. I do a lot of database stuff. Since Bodil delivered a wonderful keynote yesterday, including all the stuff you should talk about in keynotes, like the general state of the nation and the past and the future, it was very inspirational. I don't have to inspire you or tell you anything useful. I can fill your heads with useless rubbish. So that's today's program. At Factual, I'm a backend engineer. And recently I've been kind of moonlighting as a data analysis person, which means I get to ask important philosophical questions. For example, what is it like to be a fold? You all know this paper, right? It's on Qualia. Like, can we ever know what it's like to be a bat? Because bats perceive things via echolocation. Folds perceive the world, well, in a different sort of way. So, as an example, let's say that I hug this person, and then they hug me, and then we hug another person. As we hug more people, the blob becomes larger and larger. We can always hug more. More. See, we're still a group of people hugging. So together we form a monoid. All right, thank you all. Round of applause for our huggers. So, we're Clojurists. So we all love to hug. We love to fold. Fundamentally, what a fold does is to take something from every element in a collection and bring it together into one thing. Now, practically speaking, I might have a set of trades for housing in London, and I want to know what is the median price of a housing trade for a one-bedroom apartment. Or I might be I might be working on gene sequencing for a bacteria or a virus, and I want to know which types of pneumococci are present in a certain population. So I'll fold over my samples and try to determine the most prevalent serotypes. If I'm a public health researcher, I might want to know the effectiveness of a vaccine. So I'll take, say, case reports from individuals who are on a treatment regimen and who are not on a treatment regimen and try to identify if there are correlations with their behavior and with the outcomes in terms of contracting disease. I might be an astronomer and want to know what's the total mass of all the main sequence stars in a galaxy. So in Clojure, we take our set of stars, right? It's stars. We bring in our favorite macro, the double threading arrow macro, and we filter them, only those that are main sequence. We map them to masses. We reduce with plus. We've all written code like this, right? It's a very beautiful, simple. I love these things. They're great. This is the hug that brings everything to. All right. Okay. No. Right.
That's the well done one.
Yeah. I need an adult. Okay, so we've got folds that combine things. So reduces is one of these folds, and reduces a particular. Oh my God, this thing is the shortest range ever. Reduces a particular type of fold because it folds from the left to the right. So Haskell people will call this fold L. We start over here with a 0. That's our identity element, and we combine it using plus. So we add 0 to 1 and get 1. 1 plus 2 is 3. 3 plus 3 is 6. So we move along the sequence from left to right. Now, if we talk about a more complicated composition, like mapping to increments, so we take maybe the numbers from 1 to 10, we increment them, we'll get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We filter them to odd, 3, 5, 7, 9, 11, and then we reduce those with plus. So in this case, what happens? Well, these are sequences, remember? So Clojure will actually allocate a sequence to contain 2, 3, 4, 5, and so on. If you're lucky, like map, you'll get 32 element chunks, right? That's a chunk seek. And other times you'll get individual wrappers, so you have to have a wrapper that contains the number 3, and then that points to another wrapper that contains the number 5. So you can imagine, if you're doing a complex transformation of lots of intermediate sequences, you're having to allocate information on the stack and then immediately discard it. So you're putting all this pressure on the garbage collector just to produce that one number, 8. So some very clever people have come along and told us that, by the way, map is a type of reduce. You know, we here at the Max Planck Institute for Mathematical Computer Science have determined this to be true, and you can all go home now. So, so we've got this notion that reduces and maps are somehow related, that a map is a reduce. In fact, they're both instances of this thing called a catamorphism, which is a scary word that Haskell people use to intimidate lesser programmers. So catamorphisms are I'm not going to try to explain this. I'm going to do it wrong. So what we do to reproduce map using reduce is to take the first element in our reduction as the empty vector. Then we'll apply f the first element and conj it in. Apply f the second element and conj that in. And what we'll end up with at the end of this conj process is a vector that contains all the elements in the original underlying sequence, but with f applied to them. And we can rebuild almost everything this way. You can get filter, take, keep, count. All sorts of operations you would do over sequences could be thought of in terms of reductions. So we fold all of these into the reduce phase. Now, what this does is get rid of intermediate allocations. So before, where we had all those sequence wrappers holding lots of different numbers, now we can have the reducer function say, 1, well, that's incremented as 2, 2 is even, throw it away, next number. 2 plus 1 is 3, 3 is odd, keep it. 3 incremented as 4, discard it. 4 incremented as 5, 5 is odd, keep it, add it to 3, we get 8. So all of this can be done on the stack, and stack allocation is much more efficient than forcing lots of pressure on the garbage collector. Reducers was invented to solve this problem. So in a reducer, you get to do all of your work as building up transformations against some eventual reduction. And when the reduction finally arrives, it just sort of collapses all those function transformations into one, and the JIT hopefully inlines all of that. And if you haven't blown your inliner budget, things are quite efficient. Transducers does the same thing, by the way. Haskell calls this stream fusion, and I believe it is it now in the prelude? You might have to import a special thing for it, but it's a wonderful technique to make functional programs do things that would have been very fast in an iterative language in a nice, pure functional way, and still have similar efficiencies. In specific, this is a specific case of this thing called deforestation, which is a functional programming optimization technique where you try to reduce, well, forests. I'm not a mathematician. So, reducers are defined by every collection. If you go in to Clojure's core, you look at iPersistent vector or persistent vector, the implementation. By the way, does it bother people that I stands for both implementation and interface? Because I get those confused. So you open up persistent vector, and it's got this like cheerleader function inside of it. It says, like, give me an F. And you're like, F. And it says, sure, I'll apply F to every element inside of me. Yeah, 1 plus 2 plus 3 plus 4 plus 5. Yeah, we're going. And it hands back you a number. That's how cheerleading works, I think. So you take your cheers, and this is a vector, so when we build r/filter, it's saying, okay, given the vector's implementation of filter, here's how we're going to do a reduction with strings. So we'll take all our cheers, we'll find the ones that are fun, we'll put them together into the same string. All this is predicated on that specific vector implementation. If you do it on an array, you have a different type of reducer. If you do it on a seq, you have a different type of reducer. So every collection or every reducible thing in the world has an implementation of this reduce protocol. But it might make sense to reason about a reduction in an abstract sense without any real concrete underlying type. So filtering for things that are fun, that's what I do in the world, that's sort of an abstract concept, right? You could just filter anything to be fun, and then you could reduce anything with stir. And then we could apply it to this, big empty question mark later. And this is what transducers does. It is an art project to confuse Haskell people. But beyond that, it just takes the notion of reducers and gets rid of the underlying implementation of reduce. So when you say mapping inc or map inc, depending on which version of the blog post you read, the sort of natural question is, what are we mapping over? And the answer is anything you like. It's this very nice, free, beautiful, free love construct. Ultimately, you can transduce over anything, You could transduce over channels, over sequences, over people, over road networks. I don't know, it's a Florax, it's a dessert topping. There's this wonderful generic operation. But it is still, sadly, sequential. So transducers, like reducers, moves from left to right. Starts at the beginning element and goes all the way to the end. So if you're me and you have to reduce over a bunch of data files, you could be sitting there watching your 48-core machine spin all the time with one core at 100% for like 20 minutes. And you think, well, wait a minute, I have 48 cores, this should be done in 30 seconds. What is wrong? Well, the answer, you start thinking what's wrong, and the information person shows up and she asks, don't you wish there were a better way to do reductions? And you say, yes, I do wish there were a better way to do reductions. What do you recommend? Well, you go back to your childhood library and you read some books, and one of the analogies they give you is that if you're an ant, you're trying to cross a very long length of string, it's going to take you time proportional to the length of string, assuming you're a motivated ant. But if you fold the string over onto itself, if you bring the ends together, the ant can cross immediately from one side to the next. This is from Madeleine L'Engle's A Wrinkle in Time. They're talking about space-time folding, but the underlying idea that changing the topology of the space, of the structure you're traversing, can give you more efficient traversal possibilities. So what is the structure of a fold? Well, fold L, reduce, that takes the numbers 0 and 1 first. We start at the leftmost side. So 0 plus 1 is 1. Then we go up, we add 1 and 2, we get 3. 3 and 3 is 6. But we don't have to go from left to right. We could instead start at the end. We add 0 and 3 and get 3. 3 plus 2 is 5. 5 plus 1 is 6. So that's fold R, fold right. So these two things, they've got different shapes, right? And different intermediate numbers, like 3 and 5, 1 and 3. These are not the same intermediate states, but the result, 6, is the same in both cases. Why is that? Well, it has to do with the function f. If f is associative, that is to say that you could change the grouping where you put the parentheses and you still get the same results, then we're allowed to fold going from either direction. And in fact, for associative structures, you don't have to just fold one way or the other. You can actually have an arborescent fold. You can have a tree-like fold. So I could fold 1 and 2 first, and then somebody else could be folding 5 and 6. Notice that there's no line connecting these two things. There's no state connecting them. So we can do them at the same time. Because they're logically independent, they are concurrent, and they can be executed in parallel. So I can reduce these things in parallel, and then when I have to, at the end of the day, I'll have to bring them together. But the bringing together part could be cheaper than the sort of independent reduction phase. So this is actually already in reducers, because Rich invented everything, and all we need to do is rediscover it from the core library. For example, did you know there's a double-ended queue in Clojure core? Like there's a persistent queue structure. I was looking for this. I was using vectors as queues, right? And you do like a subsequence, like, oh, you can't clip off the front of a vector, right? Because it all is still allocated. The references are still there. You have to convert it to a seq, and then it's an ON convertible, right? So there's actually this double-ended queue structure that's in there, and then nobody knows how to get to it, and it's undocumented. But it totally works. It works fine. So that's. So anyway, if you go into reducers, you may have noticed this thing called fold and this function called monoid, and the thing it does is it takes the fork join framework in Java 7 and will reduce over 512 element chunks of the sequence. You want to do chunks instead of pairs because the more stuff you can read in a big chunk, the more friendly you are to the caching system. And then what you'll have is a combiner function that takes the results of those reduces and combines them together gradually. Now, this is really cool because we can reduce over lots of things in less time. If we have p reducers going concurrently, or p reducers going in parallel, we can recite the alphabet from A to N in the time it takes to say A, B. Because somebody else is saying CD, and somebody else is saying EF, and so forth and so on. So lots of processors mean we can go faster. But there's still some coordination required. The reducers fold still has to handle the reduced values. It needs to preserve order. This is a really good property. We love orderings, right? I mean, things that happen out of order are confusing. They're non-deterministic. But non-determinism is kind of bound up with parallelism, so maybe there's some negotiation, some balance to be had here. Maybe coordination between reducers is expensive or impossible. Maybe you're in a distributed system where coordination is tricky. You can often augment a non-ordered system with ordering information and reconstruct an order later. That's perfectly possible, but for the moment, I want to suppose that we try to do things without any talking back and forth whatsoever. Like, maybe we're all explorers. We send everybody at Clojure X in independent spaceships, and we land them on a planet. And our goal is to survey the planet completely. Now, I don't know where anybody else is. You're all over the horizon, and I can't talk to you because we can't bounce radio signals off of the ionosphere on this planet. So our only way to figure out the planet's landscape is for each one of us to map the stuff that we can get to independently. And then we'll send our results back to Earth, and Earth needs to reconstruct those results in a way that doesn't depend on like who was where when. Well, we can do this if the reconstruction process is commutative. If you can switch the order of arguments in your function, then the results will be the same regardless of execution order. We could merge these numbers in any tree shape we want. We don't have to preserve order anymore. That's kind of cool, right? So if you've got a function that's associative and commutative, it has an identity element, this should sound really familiar, right? Like when you were back in Catholic school and Sister Mary Holywater was explaining commutative monoids, they might have mentioned that these structures, monoids, have these wonderful composition properties. Like you can make monoid products that take two monoids and make another monoid out of them. And monoids that are commutative are especially useful for distributed systems because you can do stuff out of order in different places and then bring it together, right? Monoids are about combining stuff, about folding things together. So these are a good candidate to build large-scale data analytics systems on. There's a great talk, by the way, called on Summingbird and Algebird, and both of these are built on commutative monoids. They explain the math much better than I can. It's all in Scala, so you'll probably be allergic to it. No, it's actually quite good. Now, if you augment commutative monoids with another property, idempotence, that is to say you can keep adding the same element to the accumulator over and over again and nothing new happens. So imagine that every time Bruce hugged me, like every time Bruce hugged somebody else, they just became Bruce. And Bruce could hug as many people as he wanted, and they would all just kind of disappear inside of him. That would be idempotence. So that gives you this thing called a CRDT, which is a fantastic data structure and a topic for a different talk. What I want to talk about instead is this project I've been working on for data analysis called Tesser. And this ultimately stems from, I've got a bunch of data files sitting on disk, and I've got a bunch of data files sitting in Hadoop. I want to know information about all those data files, all the points. Like, tell me where all the people live, or tell me how many stars there are. But I want to do that reduction in parallel. I don't care about order, and I want to take advantage of Stream Fusion for performance reasons. And because it's going to be both local and in Hadoop, I want it to be collection independent. All of this is wrapped up in the same great sequence API we've come to know and love. So with Tesser, you can write map inc, filter odd, take the sum. And these operations are abstract. They don't have any concrete underlying sequence. But when you call Tesser with them, you give it some collection, some reducible things to work on, it will apply that transformation of incrementing and then filtering to the odd ones and taking the sum. It applies that in parallel across one thread per processor. The cool thing about this is that it is really efficient in cache, both in file system cache and in processor cache, right? If you do the reductions sort of en masse with a bazillion threads, you're going to pick up a whole bunch of independent parts from the files on disk. And if your files are very large, you're going to blow your page cache eventually, right? So you want to do these things as large, sequential, block, striped I/O, because the prefetcher is really good about that sort of thing. But you could take that same fold, and instead of running it locally, throw it on a Hadoop. And because it's stream fused, we can take all those operations that would have ordinarily been done in the mappers and then passed up to a reducer, we can fold them all down to the mappers directly. So the mapper in this Hadoop adapter, it doesn't just map. It actually does a reduction over everything it can get its hands on locally and emits a single reduced value instead of n values. And that can make your folds a lot more efficient. So how do you build this? Well, you take your set of inputs, and you come up with some natural division. In Hadoop, right, you'd have a mapper launched for each set of seek files on disk times the number of processors you've got available. In a local context, maybe you've got a series of data files, and each one of them is going to be a collection of inputs. You do a concurrent reduction across them, and the scheduler in Tesser will try to figure out how many of those to do at any given time. So we spawn, say, 1 thread per core, 2 threads per core, and the thread is going to pick up an element out of this reduction sequence, reduce across all the things inside of it, and then spit out a result. Once we've done that, we combine those results together using a combine phase. This is the same terminology from the reducers. Reduce is the independent phase. Combine is the sort of serial phase that brings things together. And that's the final result. It's, of course, a little bit more complicated than that. Being adherents of the Church of Hickey, it's important that we recognize the opportunity for complexion wherever possible and capitalize on it. That's wrong. No, so there are some more difficult things to think about. When we're doing the reduction, we can't just do what reduce does and take a single input argument for the initial value. We have to take a function that generates identities, because we might need to get multiple identities, one for each independent chunk that we're going to reduce over, or we might need to create an identity on each machine we're going to distribute to. So instead of having a concrete single reducer identity, we have a function that generates identities. Once we've gone through the reduction process, we have a post-reduce phase. This thing's job is to discard information. So maybe you do a reduce on a transient data structure or a reduce over a native array, and then you seal it in some way to make it suitable for serialization, or you discard some intermediate state you needed to track. This is your chance to get rid of stuff you don't need. Again, we have an identity function that's used to generate the identity for the post-reduce, or for the combine phase. And there's a post-combiner where we can discard even more information. These things together allow us to express a whole lot of sequence operations in a nice composable way. So when we're trying to build this in Clojure land, Rich has gone and written transducers, which has this kind of interesting take. A transducer is not really a new type. It's an existing type, we all know. It's a function. But it's a special kind of function that has 3 arities, that have 3 very discrete, important meanings. The zero arity form of the function, that's going to be the identity. The single arity form, that's the sort of post-combine or post-reduce phase. And then the 2 arity form, that's for the accumulator and an element being folded together. So this is a monoid, but augmented with this notion of post-completion and also with this notion of reduced abort. It's a sort of complicated beast. But it's all beautifully bound up into a single function, which is something we know how to work with, and they compose really nicely, because function composition is well understood. Reducers does the same thing, but because you've got a reduction and a combine phase that are separate things, you have 2 functions that do this arity dispatch. So there's the reducer that has a zero arity function for its identity and 2 arity form for its combine. Running out of words. 2 arity form for its reducing function. And the combiner function has a single or 0 arity for its identity and a 2 arity for its reduction. These terms are overloaded. So, Tesser, we want to combine these things as first-class elements. We can't dispatch on arity because Clojure doesn't have type dispatch. And even if it did, the types might be identical. So instead, we have a map of functions. So we've got a reducer identity, a reducer, and a post-reducer function, and then another pair for another triple for the combiners. This is about what you'd expect. The weird bit is that we don't just build those things immediately. When you call map, we can't figure out, because of stream fusion, what to return. We have to give you the possibility of mapping attached to some downstream transformation. So we actually give you a builder function that could be attached to a downstream transformation later and return the mapped version. So transducers and Tesser have this in common. When you call map stir, we give you a function that takes the downstream thing, like another map or like the filter, and then we're going to return an identity function, which will call the downstream identity to return something else. And we'll give you a combiner that calls a downstream combiner, and a reducer that calls a downstream reducer. So we're allowed to manipulate the control flow of these things and intercept them. Unlike transducers, which applies these things with function composition, we actually defer the construction phase until the very end. The reason is that you might want to do composition both inside and out. So maybe you need to wrap a transformation. In transducers, wrapping is easy. You add another layer at the outside and it will wrap. But if you need to modify the inside or modify something in the middle, you can't get to it because it's all been squished together with function composition, right? Once functions are composed, there are these opaque blobs that you can't tear apart. So we leave them as discrete parts that can be manipulated. We have a vector of these builder functions, and each operation like map or filter or take will return a modified vector with its transformation inserted somewhere in that stack. And when we're ready to evaluate the fold, we compile it by folding together the folds. And then we get back an identity map. So we have the identity, the reducer, the post-reducer, and so on and so forth. So, those of you who know me on Twitter will appreciate that we have to discuss constraints. There are specific cases where this problem is appropriate, where this library will solve your problem, and other cases in which it will not. In particular, your identity functions must be pure. So you're not allowed to do evil things in your identity function. This doesn't sound like a big constraint, but if you look at the definition of transducers, there are some sort of odd things that happen. Transducers does not use pure reduction functions. For performance reasons, it actually uses mutability. So if you look at take in 1.7, it actually sets up an atom for the number of elements that it's passed to its downstream thing, and then it will increment that every time it gets an element, and then it will call a downstream reducer. And this way, it doesn't have to wrap the accumulator value, so you're not constantly like boxing and unboxing accumulators to pass them downstream. This is a no-go for Tesser because we need all the state to be in the reducer accumulator, because then we can pass it back and forth over the network. So if the reduction is distributed on multiple nodes, you can't rely on any state you've squirreled away in the lexical context to be okay. It all has to be a pure function of the accumulator. However, we do guarantee that all of the reduction will occur on a single thread, so it is safe for you to use unsynchronized mutable values inside. So it's fine for me to take an array or a def type, anything really gross that we would ordinarily avoid in Clojure for performance reasons, shove it in there instead, and do our reduction there. And then at the end of the day, once we've finished doing all of our evil mutable things, we hide it with a post-combine or hide it with a post-reduce. The reducers and combiners have to be associative. A lot of things are associative. There are some things that are not, but if you can get away with it, it allows you to get into this nice world of parallelism, so I really encourage that. On top of that, Tesser makes the possibly questionable choice of commutativity. So just like in Freaky Friday, if you switch places with your sister or mother or whoever it was, you should still learn the same important lesson about family. It's been a while since I've seen that movie. But the important thing is you should be able to switch the orders and still get the same result. And in a lot of things, this is the case. Or you could infer the order later. So if I'm doing a bunch of observations of stars in a galaxy, I don't really need to know which observation happened first to figure out how many stars there are. Maybe each one covers a discrete range of the inputs. If I've got a whole bunch of patient report cases, they came in at different times. I don't really care how they're sorted. I can figure it out later. So in a lot of cases, commutativity is okay. This is not always the case. Algebra at Twitter is used for analytics, does very similar things to Tesser, but they think commutativity is too much to give up. You can't, or they think commutativity is too much to have. You can't give them an order. They want order. So sort of an open question, like should I impose order? Should Tesser provide you with constructs to add order to unordered things? I'm not sure yet. Like transducers, we also have the constraint that you need to short circuit when a reduced value comes in. So in a Clojure reduce, you don't have to traverse over the entire sequence. You can explode halfway through and say, hey, we're done. Everything's great here. And then the upstream transducers or the upstream Tesser folds should recognize that the reduction is completed and also abort their execution. What does it look like? Well, the good news is that you don't have to know anything about monoids, about transformers, about data types. There's no types here. Why would we want those? So instead, you get to use the same great sequence API you know and love. We map inc, we filter odd, we take 100 of those elements. Which 100? I don't know. It's up to me. I get to choose because I am the evil scheduler. That might be disconcerting, but trust me, you'll like it. So I mean, non-determinism, right? Like it's evil, but it's also like where all of our power comes from as parallel wizards. So you should embrace it. Mapcat does exactly what you'd expect, and then we can put them into some collection. All this stuff works just like the equivalent Clojure sequence program would if you called shuffle on the inputs. Which is fine in a lot of cases, right? Like if you want a sum or a median or whatever, it doesn't matter if you shuffle or not. And you can shove things into sorted maps if you want to get back sorted results. So that works fine. The important thing to note here is that take is weird. Like this version of take has no coordination between the reducers. So imagine that each one of your chunks only has like 10 elements, and you want to take 100. It actually has to figure out, with no communication, how to build up combinations from each one of those subsequences such that it could get you to 100 elements. And so it builds like a binary reduction tree over each chunk. So you get a reduced value for one element, then 2, then 4, then 8, and so on, so that if it gets enough eventually, it could like shuffle them together and add up to 100 elements somehow. That's a neat trick we can play because of commutativity. But wait, there's more. Billy Mays here with a temporal folding operator. If we want, we can build all sorts of additional constructs. You can get any element you want from the collection at random. You can remove elements, of course. That's just the dual of filtering. We can count things. We can take a predicate and determine if every element satisfies it. We can get a frequency distribution. We can find all or one element that matches a predicate with some. We can do group by, where we take a categorization function and then produce a map where the downstream reductions depend on which category your elements fell into. Min, max, and range to determine the smallest and greatest things. And those don't just work on numbers, they work on anything comparable. Keep and set, just like you'd see in the standard library. But that's not all. Thanks to Natasha, we have variance, covariance, mean, standard deviations, sums, quantiles, correlations, correlation matrices. So if you give me a bunch of records that have different fields, and you want to find correlations between those fields, you can just give me a list of fields and functions that extract them. Like, take the log of the age, and take the height, and take the person's name length, and give me back the correlations between those things. It'll give you back the n-squared matrix of all their interactions and tell you which ones are most likely to be related linearly. All of this can be done in a single pass. But that's not all. Call now, and you'll get n reductions for the cost of 1. I don't know if British infomercials are the same. Most of this may not make sense. If you watch American television, I'm assured this is much funnier. So, we can do this interesting thing with monoids where we compose them. We take a product of monoids and produce another monoid, which will itself be composable as another fold. So I can take a map of keys to folds and produce a single fold that executes all those folds and keeps track of which ones go where. So I want to know about the ages and the cities in the data set. So I'll map to ages and take the range, and then I'll map to cities and take the frequencies. So both of these take effect on the same input data structure. So a data structure that has an age and it has a city field would go into this thing, and it'll pop in here and pop in here. And then what will come out is a map that tells me that the age range in this population is 18 to 105. And the cities that we found, there were 1158 records in San Francisco and 957 in London. So we can then compose that fuse with other things upstream. If I've got a bunch of JSON files on disk, I can parse them, which could be a really expensive step. I can extract a demographic key, which involves a hash map lookup. That might be expensive. If you've spent time with YourKit, you might start to think, hey, I wish I could make these things faster by reducing the number of times I call them. That's what this is for. And then you can pass those into the fuse and get out the ages and the cities. We only have to do one parsing pass to get n analyses done. And because these are composable sort of abstract transformations, you could define like, I don't know, 50 or 100 or 200 folds, extracting all sorts of different information about your data set, bring them all together gradually, and then apply them in a single traversal. So this makes it possible to write composable, maintainable, simple reductions over large data sets that still apply in efficient manners. We can facet. If your inputs are maps that have similar types for their values, say I wanted to know the sum of all x's, the sum of all y's, the sum of all z's, but I didn't know what the keys were. If you call facet, it kind of explodes the inputs and creates a new copy of the downstream folds, one for each distinct key. And we can do this, again, because we have an identity function. We can create a sort of new state whenever we like. We have those pure reducers, right? We haven't squirreled away any state, so it's okay for us to create copies like this. So with facet and sum, I find the sum of all x's is 4 and the sum of all y's is 7. I don't need to know what the keys are in advance. To recap, Tesser gives us stream fusion. So we avoid having to do extra allocations by putting more things on the stack. We have a collection-independent API, so you talk about transformations in the abstract, and then apply them either locally or in other contexts like Hadoop. All these executions can proceed in parallel. We can do parallel reductions and only have to combine things that are much smaller. This helps us get work done faster and take advantage of multi-core systems. Tesser is commutative. Maybe a good choice, maybe a bad. Come tell me later. It also offers all of this stuff in a sequence-like API we've come to know and love. So you get to call your double arrow tongue operator. You pass in something to the head of the snake, and it swallows it, and it goes through all of these transformations and comes out the end, and there's your data. This is a nice composable pattern. It reads top to bottom. I find it's really helpful. There are other systems you could use. You could use Narrator, for example, which has another very beautiful API that looks completely different. You could use Algebird, which is in Scala. There are lots of different ways to explore this monadic idea, and I encourage you to look at all of them. So, this work is thanks to Natasha Whitney and Zach Tellman, my coworkers at Factual. Tyler Schuett and Brent Ganetta helped put together the presentation, and I'm also indebted to Bruce and to everybody here for putting on such a wonderful conference. I'd like to thank you all very much for attending and listening to the talk. So, code is available at github.com/afer/Tesser. This is a collaboration between myself and Natasha Whitney. Current status, as of right now, it is released on Clojure. You can play with it. The core library is tiny to keep the dependency size low, so you can include it in your stuff and not have to worry. The Hadoop library is not yet extracted from internal use. It's been in production for 4 months and is relatively stable, but it's hard to generalize, so I'm still pulling it out. Math library is almost done. Quantiles work. The only problem is that histograms are not quite ready yet. So all this stuff will happen hopefully as soon as possible. Any questions? Well, count is relatively straightforward because it uses constant size, right? If you want to do like a cardinality estimate, then you can use hyperloglog. I have not actually written the stream for it, but it's really trivial. So Streamlib is one of the dependencies, and we can just throw stuff into QDigest or AVL tree digest or hyperloglog. Yeah. Mm-hmm. You are, of course, free to violate those constraints at any time, and I encourage you to do so with interesting results. The question? So Tesser gives you the transformations, and the transformations could be applied in any context. So, sorry, the question, to repeat that, do you need Hadoop to run this in distributed context or not? The only adapter I've written for a distributed system is the Hadoop adapter. However, it's only like 60 lines of code. So the only thing you need to know as an implementer for Tesser, like adapting it to a new system, is how do I take that map of those 6 functions, you know, the identity and the reducers, and how do I get that into the distributed system? Once you've done that, you can reuse all the same compositional folds. All those things are reusable. So hopefully it will be relatively straightforward to extend to other systems. I don't give you anything out of the box. Yes? If you get reduced values from different reductions independently. So because there's no communication between the reducers, and this is because they're being scheduled by Hadoop, and I have no control over that part of the phase. So locally, what I do is I optimize early. As soon as we get any reduced value, every other reducer aborts as soon as it sees that. And we could abort even sooner. You do have to be side effect free because we can't guarantee that we can reach and interrupt the other reducers from doing their work. In Hadoop, every node, every mapper will proceed independently until it has reached a reduced state or completed its reduction. The combiner, depending on the order in which it sees its results, could do arbitrary things. So in practice, like the take fold is only going to give you tops 100 elements, right? So every single reducer is going to stop once it hits 100 elements. We don't have unbounded time, but we do have to wait for every single one of the reducers to go through and do it in Hadoop because there's no communication to abort. We'll see whatever values pop out of the post reducer, and the post reducer sees whatever pops out of the reducer. So if you emit a reduced value, it looks the same as if you'd gone over the whole collection in the chunk and just completed early. That should be transparent. You can emit a reduced at both stages. So you can emit a reduced in the combiner as soon as you're satisfied, but you get the opportunity to inspect every single reduced value if you like. It does not use fork join. The reason is that the fork join pool has exhibited some really weird contention effects in my tests. I've got a 48-core box for a desktop at this point, and it shows up some interesting properties of the fork join pool. Like only 4 or 5 threads running in a fork join that should be 48. I haven't figured out why. It might be a GC thing. It might be a fork join thing. What I found is that by doing actual real threads, I can go way faster. So that's what it does right now. Yes. So you do not have to implement anything besides reducible to get the advantages here. So the only requirement that Tesser has is that your objects be reducible. It needs a collection of reducible things as its chunks, basically. And the way it works in Hadoop actually is we use parkour, which exposes a reducible interface over the local mapper. So it's really straightforward. You can use the exact same reduce on your local collection and on a parkour collection because both of them have the same protocol. All right. Thank you all very much.